want to get started right away with our wonderful conversation today, Uncertainty Across the Arts and Sciences. I'm Suzanne Marchand. I'm LSU Systems Boyd Professor of History and one of the founding members of the Center for Collaborative Knowledge, or CCK. And I want to welcome you to this webinar today. Thank you so much for attending. For those of you who don't know of the work and mission of the CCK, let me explain that the CCK is an LSU organization whose purpose is to increase cross-campus conversations in the hopes of reminding us of the riches of knowledge that lie right here on our campus in Baton Rouge and in our medical school in New Orleans. On behalf of the CCK and of the Uncertainty Planning Committee composed of myself, Professor Inessa Bazayev, and Professor Aaron Sheehan-Dean, we would like to warmly welcome you to this series on uncertainty across the arts and sciences. Today's first session features a world-famous jazz and class pianist, a path-breaking researcher in psychology, and a professor of chemistry, inventor, and sometimes guest editor for a journal entitled Chaos. We are all in for a treat. Before I offer a few more introductory words to our series, I would like to offer some thanks to all the participants who enthusiastically agreed to share their knowledge and wisdom with us, and to the co-sponsors of the series, the Eric Vogelin Institute, on whose website you can find information about the series and links to the participants' web pages, and the Office of Research and Economic Development. And I would like most especially to thank Stephen Beck, Holly Carruth, and Julie Perkins for their help. We would also like to thank Leah Moore, Administrative Associate in the History Department, for the design of the beautiful invitation and for sending it out to all of you. We are also joined today by several representatives of the National Academy of Sciences branches of the Same Tree initiative, and I'm most happy to welcome them virtually to LSU. In fall 2021, we will also put on a big show when they come to campus in person. Finally, I'd like to announce that in addition to the other two already planned sessions of this series, we will add a fourth, entitled Uncertainty in Louisiana's Future, organized by Professor Craig Colton of the Department of Geography and Anthropology, and featuring as speakers Professor Colton, who is an expert on Louisiana's waterways and flooding, MacArthur Prize winner and specialist on oceanic dead zones, Dr. Nancy Rabelais, and distinguished architect and professor of architecture, Dr. Michael Desmond. Invitations for that event will go out shortly, but please mark your calendars for that Zoom event on Wednesday, April 14th, 3 to 4:30 p.m. And now for a few thoughts to launch this series, Uncertainty Across the Arts and Sciences. Uncertainty these days seems the name of the game, the fundamental reality of all of our existences, whether we are discussing infection rates, school and business reopenings, tech futures, or travel plans. Undoubtedly, in the last year, our world has come to seem, and perhaps even to be, more uncertain than ever. But in point of fact, human beings have always lived with uncertainty and always known that. In his histories, completed about 430 BCE, Herodotus, the first proper historian and a great favorite of mine, has the wise philosopher Solon tell the foolish, vastly wealthy King Croesus that life is so very unpredictable that no man should count himself lucky until he is lying on his deathbed. Arguably, all of the world's religions exist to cope with the uncertainties of this earthly life. When we enter into the realm of knowledge, all the sages agree that far more is uncertain than is certain. And the greatest error one can make, and the one most likely to get you into trouble, is to say that you know something for sure. One might even say that certainty breeds complacency and even ignorance. Where would the human race be if Eve hadn't said, "Hey, Adam, shall we just see what that apple tastes like?" As our distinguished group of experts from across the university will, I believe, abundantly demonstrate, uncertainty is a precarious and frustrating condition, but it is the one that we earthly beings can know, and that, in the end, isn't such a bad thing. Coping with uncertainty is just what mortals have to do. In fact, uncertainty may well be the principle that makes knowledge and the university as we know it possible. Uncertainty generates creativity, curiosity, and the desire to know and see more. It is the very wellspring of the principle of research and of the scientific method, which starts from a position of hypothesizing, not one of knowing. Uncertainty is critical also in the arts. As Immanuel Kant knew, the artist or composer cannot possibly create something beautiful just by following a prescribed set of rules. We might do well to embrace uncertainty and to celebrate the ways in which it is inseparable from all the scientific, humanistic, and artistic efforts we cherish as a society and we share with students and colleagues at universities such as LSU. In this series, we will hear from experts across a wide range of disciplines and from persons who wear many hats, from an expert beat reporter to a veteran physicist, from a Nobel Prize winning experimental physicist, to a world famous musician who modestly calls himself just the piano player. We will hear from scholars who innovate in memory studies and those who concoct chemical experiments, from the deeply learned humanists who have inspired hundreds of students, and from the LA State climatologist. Who better to explore that fundamental uncertainty? Will it rain tomorrow? This will be, I believe, a fascinating meeting of minds, of those who all too rarely meet. And I hope it will be the starting point for many more cross-campus conversations of the sort that the Center for Collaborative Knowledge seeks to generate. We will begin today with three distinguished colleagues: Boyd Professor of Music, Willis Delony, Professor and Chair in the Department of Psychology, Emily Elliott, and Professor and Chair of Chemistry, John Pojman. I will introduce them sequentially, but only briefly, to allow maximum time for their presentations and for general discussion. Links to the speakers' web pages, which detail their many achievements and honors, can be found on the Eric Vogelin Institute website, which I believe Inessa will put in our chat box for your convenience. Each speaker will have approximately 15 minutes for his or her presentation, and we will simply follow the order of the program, with Emily following Willis and John finishing the formal portion of today's session. After John Pojman concludes, we will open the floor for discussion through the Q&A function. If you would like to ask a question of one or all of the speakers, please type your question in the Q&A box and we will convey it to the participants. If you are an LSU student, please note that in your question and we will get your remarks, give your remarks priority. At the end of the session, please stay tuned for a brief notice about coming events, including the next two sessions of our series and tonight's Science Cafe presentation at 6 p.m., which we hope that you will attend as well. But now, without further delay, let me introduce our first speaker, Willis Delony, Boyd Professor of Piano and Jazz Studies at Louisiana State University. In a performing career of more than 40 years, Professor Delony has earned acclaim as one of the nation's leading classical and jazz crossover artists. He has appeared as a piano soloist, guest pianist, and arranger or conductor throughout the United States, as well as Canada, the former Soviet Union, China, Mexico, Costa Rica, Argentina, and Brazil. His innovative piano explorations have been showcased in a dozen solo and collaborative recordings, including the recently released, just February 16th, recording of the Jazz Concerto for Piano and Wind Ensemble by Greg Yazinitsky, which features Delony with the LSU Wind Ensemble, conducted by Damon Talley. His presentation today is entitled Making Music and the Art of Painting Yourself Out of a Corner. Take it away, Professor Delony.
Thank you, Professor Marchand. And good afternoon to all of you. I hope you can hear me well, and maybe one of our panelists will give me the high sign to make sure I'm coming through well. Good. As Professor Marchand noted, my talk today is Making Music and the Art of Painting Yourself Out of a Corner. Now, I stole that expression, painting yourself out of a corner, from a colleague of mine who once told me, He said, Willis, the thing I like about listening to jazz musicians and watching you guys perform is that inevitably you paint yourselves into a corner. And it's so much fun to hear how you paint yourself out of it. And I've always enjoyed that particular image in my head, and I'm kind of proud of that, actually, that he thought that was a compelling reason to enjoy what we do as jazz musicians or classical musicians or musicians in general. Uncertainty is part of what musicians deal with, perhaps subconsciously. I'm not so sure we think about it so much. I've been thinking about it a lot more because I've been asked to do so. But whether we're composers, performers performing from a notated score and all the preparation and practice that that involves, improvising from a set of guidelines like jazz musicians do, or improvising with a complete freedom and no structure and no guidelines at all, that's valid too. Whatever level of musical expression is involved deals with some degree of uncertainty. And today, I've planned, I've got a little outline here in front of you, but I have no idea how this is going to turn out. I prepare a lot, I practice a lot, but I don't always follow a script once we get started because sometimes that script doesn't seem as relevant. Maybe it does today, maybe it doesn't. But for musicians, we practice a lot. We learn lots of musical vocabulary, theory, technique, historical references, so that we can make sure that a certain kind of unwanted uncertainty can be eliminated from our performance. And by that I mean the kind of uncertainty that you can't really manage. It's that negative kind. It's the kind you're not prepared for. And I would say that if our musical vocabulary is not sufficient to deal with the accidents that happen in a performance, then that's the kind of uncertainty that's not going to be successfully managed. But inevitably, in a musical performance, even if I'm playing a classical piece, say this beautiful phrase by Johann Sebastian Bach. I've played that piece 1,000 times, and I can probably play it 99% perfect in front of a friendly audience, maybe even a hostile audience. But I've done it enough. I think I'm ready to go. But you know something? I always miss notes. And the question is, what if I play a real stinker? You'll hear it. Pretty sour, wasn't it? Now, do I go back and say, oh, I'm sorry, folks, I got to start over so that I don't do that again? I didn't expect that to happen. That's kind of the uncertainty, but you know, it's bound to happen somewhere. Unfortunately, it happened in a spot where everybody can hear it. Do I go back and start over again? That's not a good thing to do. And what if I were playing with 2 or 3 other people? You know, can I say, hey guys, we got to stop. I missed the note. I want to get it right this time. No. Maybe I need to adjust for the moment. Maybe I know enough musical vocabulary. I sort of made the wrong note more right and insisted on that wrong note. Damn it, I'm going to play that note. It's what I meant to play. It's not what I meant to play, but I'm going to try to fake it till I make it, right? But if I didn't have any vocabulary to fall back on, I would have not been able to manage that particular situation. It happens even in a classical piece that we've rehearsed, practiced for hours and hours. Sometimes one has to adjust. As Professor Marchand noted, I'm a classical player, but I'm also a jazz player. I'm kind of like a musical schizophrenic, you might say. Bipolar musician. Spend half my life in one world or the other, but I find it fascinating to see how these worlds connect. Granted, one would expect that if you're considering a jazz setting, there's a certain level of uncertainty that's a given, right? Jazz musicians improvise. In the moment, we make new music happen that we've never played before. So there's a given, right? It could be a blues musician, or it could be a gamelan orchestra from Java. You know, whatever culture you're referring to, most of the music of the world is improvised. So there's a certain uncertainty. That's probably not a very good phrase. Sorry, English folks. But there it is. Music is communication, like language. And sometimes we speak the language of music in the moment. And for us here in the United States, in the Western world, the emergence of jazz as a musical language over the past 100+ years has allowed us an avenue to express ourselves musically in the moment, dealing with uncertain results at the end, but inside a vocabulary that allows us to express ourselves the same way we express ourselves with language. If I have a conversation with one of you, I don't rehearse what I'm going to say to you ahead of time, nor can I recite what I said to you today, tomorrow. No, we just talk. It's because we have a vocabulary to communicate with. That's what jazz musicians do. Let me try to demonstrate how this might be interpreted. Here is a tune that jazz players like to play, and I think it's an apt choice for today. The title of the tune is Alone Together. There's your metaphor for today. Eventually we're going to be together, but sometimes we're alone together because I'm here, you're there. Another layer of uncertainty is I don't know how this is coming across to my audience. I'm used to an audience, but I haven't seen one since last March, so I may be absolutely ridiculous right now, but too bad. You can't get to me from there. Here's the tune. So there was a melody. Somebody else wrote that melody. I interpreted that melody in a jazz style. Now let me take that melody out, and I'll just play those nice pretty chords. One of my teachers called those Saturday night chords. I happen to play them. And on any day that ends in D-A-Y, I play those chords, so I like them. So I took the melody out, which is what jazz players do, and then we make up new melodies. I've never played that before. I didn't know how that would turn out when I started it. But I've practiced that tune a lot. I've played it 1,000 times with colleagues. I know what fits over that chord. I know the theory, in other words. Other possibilities. I've never played that before, but it falls in line with what I know fits with these chords. Uncertain result, but I'm fairly certain that it's going to be okay because I was within the confines of the vocabulary of that little snippet. But what if I paint myself into a corner? Then what do I do? I love this story about Herbie Hancock, the great jazz pianist, who was playing in Miles Davis, the great jazz trumpeters group. And Herbie said, I was playing something and I got to a section where it was so spectacularly awful. He said, I'm paraphrasing, but I think Herbie was really embarrassed that he was playing something so bad. But what did Miles Davis do? Well, Miles Davis picked up his trumpet and he started playing some of those wrong notes that Herbie Hancock was playing, and just kind of validated Herbie as a person and made those wrong notes suddenly the true context of the moment. Isn't that a great story? He made those wrong notes okay. He dealt with that particular moment. He painted Herbie out of a corner. Now, I can paint myself into a corner with the best of them. I miss lots of notes. Now, those notes work great. Those notes don't work too well, and I might accidentally get there in a performance and have to do something about that. Not be able to tell, but I was playing all kinds of wrong notes on purpose, but resolving them hopefully to something that fit. It didn't sound very good. Actually, in the moment when those accidents happen, I probably sound better when I make the adjustment than when I'm trying to purposely make a mistake. Does that make sense? I sound better when I make a mistake accidentally than when I do it on purpose. There again, I can't see how the reaction is out there, but they probably think this guy's completely out of the box. But in jazz performance, we do have some structure involved most of the time. If I got my timer on, excuse me. I'm doing pretty well here. Got 3 minutes and 12 seconds. Musicians don't necessarily have to rehearse that tune. If they know the vocabulary, we can sit down and play. If I tell somebody I want to play a blues in B flat, well, my jazz friends will know. Something like that should happen. I've never played that before, but I've played something quite similar jillions of times. The logical question some might ask is, what about improvising with complete freedom, with no structure at all, no guidelines? What happens then? Well, I would say that if I do that, my vocabulary will automatically take over. If I have some musical sense about me, if I say my right hand's going to react to my left hand or vice versa, I'm going to do something with my right hand and my left hand's going to react to it. It might be okay. So let's say I got 2 notes in my right hand, 2 notes in my left hand. Now 2 notes. And maybe 3 notes. Go from there. That was free improvisation, but it was sort of intelligible because I was using a certain kind of vocabulary, in this case jazz harmony. But what if I wanted a kind of a Bach-like? Something, now that was gibberish. gibberish, Emily. That was musical gibberish, but it was kind of a quasi-Bach-like improvisation. Free, but using a specific vocabulary. See, I couldn't do that using language if somebody was speaking to me in Russian, because I know 2 words in Russian. So I can't have a conversation. I can't express myself in Russian, but my musical vocabulary is large enough that I can make something happen. I can prepare something from a score and deliver it and hopefully give it some meaning, or I can improvise on the spot and perhaps do the same thing. It's the way I express life in many ways. And of course, I've been made to think about how uncertain this enterprise sometimes is. So let's open the floor for questions.
Thanks so much. Willis, we're going to wait on questions until the end, but there will be plenty of questions, I know. That was just beautiful. I wish we could all learn to paint ourselves out of a corner as beautifully as you've shown us how to do. We'll now move on to our next speaker, Emily Elliott, professor and chair of the Department of Psychology. Professor Elliott is a cognitive psychologist who specializes in the study of the development of memory in children, as well as how children and adults process sounds in our environment. She's especially interested in the implications of distraction on our cognitive performance. Her screen share just moved my remarks briefly. Excuse me. And now I'm back to them. I got distracted, Emily. She was an undergraduate psych major at LSU and has been a faculty member at her alma mater since 2002. Emily's also a fellow of Division III of the American Psychological Association, and just last year in 2020, she served as president of the Society for Philosophy and Psychology. Her presentation today is titled Open Science Methods and Practices, A Psychologist's Journey. So Professor Elliott, the floor is yours.
Wonderful. Thank you so much. And I'm going to go ahead and progress this into the official screen sharing mode. Hopefully this is coming through and you can see it okay. And sorry for that distraction there. I did not plant that, although it worked pretty well. So this is going to be a little bit different, but Willis, that was an amazing presentation and you gave us a lot to think about. And I'm going to try to think about ways in which the vocabulary of music translates to long-term knowledge and memory and see if we can't make some connections across these. So I'm going to just talk a little bit today about really a journey. Going into open science as a way to communicate about uncertainty and as a way to try to make what we do more public so that people have questions maybe about how things really work in science or how individual factors like bias, because we're human beings, how that can come into play. And so by having open science, we try to address uncertainty a little bit. And so just to take you on my journey, it all started in 2017, and you might see these very adorable children in this picture. Those are my children, but a few years ago. They're a good bit older now. And I study memory in children, so it's kind of cool having 3 subjects in the house at all times. But they helped me also to pilot test some of this material. And so what we talk about a lot in my field is that we know some things, right? We have some certainties. One of our certainties is that children's memories improve with development. Boom. I mean, no one will argue with that statement. Now here comes the argument. Why? Why did they improve with development? Well, there's a lot of different ideas. And one of them is that young children do not rehearse and older children do. And so what does that even mean? Well, as an adult, for example, if a car goes speeding by and you want to remember the license plate number, you're going to almost automatically start reciting the license plate in your head. You know, if you had your phone out and you could take a picture that fast, you maybe would. But most of the time, we don't have that capability. So we say things over and over again to ourselves in our heads. And the idea is that it maintains the information, it keeps it fresh and accessible, and it allows us to have that memory for longer, right? But young children don't necessarily do this, but older children do. So the child wearing the green shirt in this picture would be classified as a young child because he's definitely older than 7. right? And so the idea of one of the major theories of how working memory develops is that around 7, there's structural change. So the girl in the blue shirt is probably hitting that structural change in this picture, and the girl in the pink shirt's way past it, right? So the pink shirt, she's got this. She's got rehearsal down. She knows how to remember a series of pieces of information, whereas especially for the boy in the green shirt, probably not. So this idea has been really discussed and debated a lot in the field. And so what we decided to do was go back to a classic. So in our field, there's a study done by Flavel, Beach, and Chinsky in 1966. And this study says what we know about rehearsal is that children who are younger don't show overt evidence of verbalization, but children who are older do. So to walk you through this table, what you're seeing is that the kindergarten children, 18 out of 20 kindergartners, were shown 0 times to do any kind of verbalization. So you show them a series of pictures, you ask them to remember the pictures in order, and along the way, are they saying anything out loud? And the recall response here is pointing. So they're not asked to say anything, they're asked to point. I saw this pencil, I saw this apple, right? But the kindergartners don't say anything. Whereas if you look at the fifth graders are speaking much more frequently. So that 3+ column, if you go down to the 5th grade row where it says 13 out of 20 fifth graders verbalized 3 or more times. And how many kindergartners did that? 1. So this was striking. This is when we talk about an effect size, the difference between what the kindergartners were doing, which was not verbalizing, and what the 5th graders were doing, which was very clearly verbalizing, led to what we considered a large effect size. And so this was huge, and it's been cited well over 1,000 times. When people talk about what we know about development of memory in children, they say, this study, this is what we know. This is how we know it. Okay, so we were talking about this, my colleagues and I, and we said, well, do these findings generalize? Who else has done a study like this? Well, it turns out there was only one existing near replication of these findings, and it was done by the same lab around the same time. So some of the same researchers in the mid to late 1960s, right? And many other research studies have been done since that time, and they support the gist, the idea that maybe older kids are doing things differently than younger kids, and that's what's supporting their memory. But it was never direct, it was always indirect. And again, thinking about uncertainty and what this means, well, how do we know what we know? How do you define your research problem? How do you know whether someone is rehearsing or not? You can't necessarily see that. So the original research focused on children's mouth movements because rehearsal is hard to quantify. So we show children pictures, we ask them to point to the pictures that they saw in order, and that's our input and our output. We've got input, here's pictures. Our output, they point in the order that the pictures were presented, either correctly or incorrectly, or they just don't respond at all because they're kids and they're just to get distracted. And so we've got that input and output, but what's happening in the middle? It's in a black box. And so how do we take that and translate it into something that we can use to understand what we know, right? So this study, the hallmark, the classic of our field, was based upon this idea that if you can see them moving their mouth, it must mean they're rehearsing. And so my colleagues and I wanted to understand that and wanted to understand it in the terms of where we are in science today, which is trying to make things more open and trying to make things more public. So what we did was we moved to this idea of a registered replication report. And some people may have heard of this, some people may have not heard of this, but the idea behind it is it's no longer the lone scientist in the tower, and then they come out and reveal their brilliance to the world. It's a team, and the team says, I'm going to register what I'm going to do before we even do it. And we're going to replicate to try to prove whether an existing study can be done again, and can we find the same thing. And we're going to do it in open methods. We're going to use as many tools as we can that are free and available to the public. They're not behind a paywall. They're not behind a .edu email address. And we're going to reach out to some labs, see if they want to participate, because the other aspect of this is if one lab is finding something and they're repeatedly finding it, that's great for them. But what if there's something unique about their lab, or maybe there's a bias that hasn't been uncovered? If multiple labs participate in multiple locations and you're still finding it, then that's going to be a good thing. So the idea was, we said, hey, people that we know that do research with children, would you like to do a really difficult study without any money? We were afraid no one would think this was a good idea. But what we did by having this registered replication report was, the idea was, if we can get this manuscript accepted up front, we write down everything we're going to do. If you participate, you can have authorship. We're not going to give you money, but we'll give you authorship. So that's how it was set up to get people to participate in this. So we had to pilot test, and we had to develop the protocol, because it had to be completely clear to everyone that wanted to participate without us like having a bunch of meetings. It had to be something we could post online and people would understand. So at the beginning, there were 3 labs involved. My colleagues, Candace Morey and Angela Aubuchon. Candace is in Cardiff. Angela is in Omaha. And then this is actually one of the undergraduate researchers, Gabrielle Toops, who was involved in this project in my lab. That's there in Audubon Hall. And the idea here was, even from the beginning, this was an international project. So we needed lots of free and open materials, or there would have been no way to make this work. So what we did is we wrote what we call pre-data manuscript. So we started in 2018 with this submission. Remember, the idea was born in 2017, took us until August of 2018 to get every literal detail written down where it could be shared publicly. This went to a journal, and it was accepted provisionally in December of 2018. Then we publicly made that call to say, if you participate and you do all the things you're supposed to do according to this protocol, you can be an author on this. And we gave people a deadline, which turned out that was plenty enough time between December and January, and then a year to collect data. Why so long? Because we needed children in kindergarten, 1st grade, 2nd grade, and 5th grade. And they had to be a very specific age range, because it had to be replicable across all of the different locations. And fortunately, it was all done. All of the data were collected by January 15th of 2020. We had no idea what was coming in 2020. So it was very, very fortuitous that all these data were in, because getting kids in person in the lab after this date would have been really difficult. Okay, let me show you what a pre-data manuscript looks like. So talk about open science. You write your paper before you've done your work to know the results. So we had to use conditional language. And so this is the actual abstract that was accepted for provisional publication. And so we have things in there and highlighted in bright yellow to indicate when we had no idea what was going to happen. So talk about uncertainty. This replication report relied upon, don't know how many labs, because we don't know who's going to participate. And what we're trying to do is find out if this pattern of findings from the original work will be upheld. We don't know if it will or not. So we wrote language that said it either will or it won't. And then after the data would come in, then we would go back in and change that language. Very different way of doing things. So let's get some numbers. What actually happened? Well, we originally received 22 labs who indicated that they wanted to participate. We had the program was created here at LSU. Like I mentioned, my children were pilot subjects in this program, and then it was translated to 6 other languages and is completely publicly available. So the software is free. It runs through a browser, and we posted it on the Open Science Framework website. So anybody who's interested in memory tests, there are some child-friendly memory tests in 6 languages for free that are available. 17 labs completed data collection, so from start to finish, and made the deadline. And then we ended up with 977 children. So the original paper had 60 children, just to put that into perspective. So almost 1,000 children in this study. And so this is a very exciting and colorful picture. So let me walk you through it. If you look at the bottom right-hand corner of your screen, you should see a box that says original. In the original box, what I want to draw your attention to is the lower left-hand corner has a bright purple square. Okay, and then as you move across, you see that it's yellow. And then that same original box, the upper right-hand corner has a lighter purple, right? So that's your pattern of data. That's your heat map. So use that original box as your template and then look across. Do you see that in any of the other boxes? Not so much, right? So what you see in the original was the 5-year-olds basically never verbalized, and the oldest children were most likely to verbalize. So that striking contrast between the original findings was not exactly upheld. So pick a box, any box, what you're looking for is dark purple all the way in the lower left, you're not going to see it. You're going to see lots more gradations of color. So this is one way to visualize data from 977 children all at one time. So it takes kind of a lot, but you're basically looking at color patterns. Okay, let me put this in a different framework for you. So what you're looking at here is the different locations. The original lab is at the top, and then that dotted line in the middle is your 0 point. So if there was no difference between how 5-year-olds behaved and how 7-year-olds behaved in this task, it would be sitting at 0. And so what you're seeing is for the top line, that flavel et al., it's off to the right, and that's your effect size. That's saying 7-year-olds give a lot more evidence of verbalization than 5-year-olds. But going down the line, all the other labs didn't find exactly that, but they found evidence that's still to the right. So your main effect is still saying, yes, there was an increase in verbalization from 5 to 7-year-olds, but just wasn't as strong as the original. And then the same format, this is the comparison of the 7 to 10-year-old children. You're seeing a whole lot of squares that are falling on that dotted line at 0. So this is saying your effect size, the difference between 7 and 10-year-olds is not very large. So we did not see a significant increase anywhere near the scale of what was found in the original. So what does this tell us? We go back to our pre-data manuscript, and we had this highlighted text to say, we don't know what's going to happen. And then now we're writing it in. The text underneath is what actually happened. So there were 17 labs, there were 977 participants, and it was sort of upheld, right? So in general, younger kids speak less than older kids, but the original study had 10% of the 5-year-old group verbalizing, and ours shows 76% of the 5-year-old group verbalizing. That's pretty substantially different. So final thoughts. Whew, this was a huge project. I'm like exhausted when I think about it, but I'm exhilarated because there's never been anything like it in my career where you could do a study with 977 children in 6 languages for free, basically, except for people's time. And it would never have been feasible without open access. So perhaps open science can help us to deal with uncertainty, but I would definitely argue that not every dependent variable is the same. And a lot of what we have to think about in psychology is we study things that are not necessarily always objectified in the same way. And so if I'm saying I'm studying memory in children, even that sentence can mean a lot of things. So in this case, we were studying immediate memory for objects in order, right? That's so different from when Dr. Delony was talking about his vocabulary and his music, his long-term knowledge of theory, of what a Bach piece is going to sound like relative to a jazz piece. That's drawing on your long-term knowledge, right? So then that's a different kind of memory than memory in the immediate short-term sense. So my point is every dependent variable is not the same, but some dependent variables like memory for objects in order lends themselves really well to open science. And open science may help us to deal with some of these uncertainties. So I'd like to take just 2 more seconds to thank the team. These were all fabulous undergraduates who helped us. We had to have multiple people with each child because someone had to be watching their mouth while somebody else was running the memory experiment on the computer. And I'd also like to thank you all for listening and to thank CCK and the Vogelin Institute. And to just give a second to give a full shout out to all of the authors from the 17 labs. This is definitely the kind of thing where if anybody has questions about details, totally I can share that information later. And I will stop my share.
Thank you so much, Emily. That was terrific. I'm already starting to see some connections across fields. I hope you are as well. I think we'll see some interesting resonances maybe when Len Apgar talks about fake news and open citizenship reporting, and perhaps some interesting thoughts with also the relationship between practice for medical purposes and what Willis said about training your vocabulary for music. So we're starting to build some interesting ideas. I hope you're also building some questions. And now I want to introduce our final speaker, and that is John Pojman, professor of macromolecular science and chair in the Department of Chemistry. Professor Pojman is a specialist in polymer chemistry and has made some 279 presentations, received 2 patents, and co-curated an exhibition at the Louisiana Museum of Art and Science. He is the co-founder and president of Pojman Polymer Products, LLC, which manufactures 3P Quick Cure clay and 3P Quick Cure wood filler, which I have had the privilege of seeing experimented upon in my very own backyard by my son, Henry. He also takes a special interest in aquatic salamanders of Louisiana, and I have met his aquatic salamanders. I can testify that they are indeed in the tank in his office. And he boasts the world's largest collection of pocket protectors. Today, he will address the question, epistemological implications of chaos theory. Professor Pojman, please.
Thank you very much, Sue. I love saying epistemological. I think it's such a great word. And so it's rarely I have an opportunity to give a technical talk and combine it. But I've long been interested in this idea of chaos, and it's a word that's used, and we're going to define it rather specifically in our context. But already from the idea of improvisation, I realized that a really nice example will come here from the beautiful piano playing. So when we talk about chaos, we don't mean randomness, and we'll distinguish that from, say, noise. When Willis talked about playing the piano, he wasn't randomly hitting notes. He was doing it within some kind of structure. And so we'll see something like that here. So it's not random, which is just noise, but it's still not periodic. So there's it never will actually repeat. It's also deterministic, and we'll spend a lot of time emphasizing what that means. And it's also extremely sensitive to the initial conditions. And that will be important then for the concept of prediction. So let's just give a comparison here. On the left, we have something that is actually a random signal. And if you were to listen to that, that would be white noise. On the right, we have something that, well, it's not quite clear looking at it if it's periodic or not. But in fact, we can use an analysis to determine if it's periodic, something called Fourier analysis. And in fact, you can get some wonderful apps for your phone. I'm sure a lot of you have these, a Fourier analysis program that you can listen to around your house and listen for certain signals that are happening in the noise in your house. And if there's a fan or something, then you'll hear the certain frequencies corresponding to it. And this is how noise canceling headphones use this Fourier analysis. But look at that signal that was periodic, but it actually has a noise added to it. But the Fourier analysis shows there's just one frequency to it. So that's how there's a mathematical way to determine if something is periodic or not. What does it mean to be deterministic? It means you can write down a set of equations to describe the behavior of the system. And that's sort of similar to Willis mentioning that he has certain rules, he has knowledge of piano, there's certain ways you do it, that it's not simply random playing. But here we'll mean this very specifically, because one of the great goals of scientists is to create a model that will predict the behavior of a system. So this really was really important. Pierre Laplace, he created the idea that people call it Laplace's demon. And we now talk about sort of the clockwork universe, that you can regard the present state of the universe as the effect of its past and the cause of its future. An intellect which at a certain moment would know all the forces that set the nature in motion and all the positions of all the items of which nature is composed. If this intellect were vast enough to submit these data to analysis, it would embrace in a single formula the moments of the greatest bodies of the universe and those of the tiniest atom. So this was the idea that was very popular among deists, was that there's a clock, and maybe there was a being that started the clock, but then it just runs forward. So we'll see, can we do that for our systems? Well, I'm going to show you a very simple counterexample. It's called the logistic map, and it's a very simple mathematical expression that says, tell me the population you have now, and we'll do it between 0 and 1, but it represents the population, say, of organisms. And I'll tell you with this model how many you'll have in the next generation. Right? So very simple. And I remember doing this in 1983 as a junior in college and taking a course in this on mathematical modeling and using a calculator that didn't have any memory, and it was incredibly crude. And I would do this over and over again, and we would see some very strange behavior I'll talk about. Now it'll be very easy. I can show you exactly how we can solve this. I'll demonstrate for you in a moment something called sensitivity to the initial conditions. And mathematically, if you'd like to see this, it says if there's a little difference between, you do the experiment 2 different times. In one time, you're just a little bit different in your initial conditions. That little difference will grow exponentially. So it means it'll always get bigger and bigger and bigger, 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 and eventually be infinitely big. So that's a feature I'll demonstrate here. So this is the model. It describes how the population will grow. That's this growth factor. If there were no crowding, the population would just grow and grow exponentially. Instead, we put in some crowding factor, which means the population can't grow infinitely. So now let me switch and actually share now a wonderful online site that allows you to solve these equations. I had to do it over and over again in a calculator, one step at a time, but let's take a look here and see. This shows the population. If there's not enough growth, it will decline. But now we can just increase the, now this, to restart it. All right. If the growth rate is too small, the population will die out and you have extinction. And I'm doing here is just changing this growth factor lambda. And again, we can eventually get to a steady population. And if we make this growth bigger, the population, again, it reaches a steady value. Very boring. This is just constant population. But it gets interesting as we increase this. And notice here that we can start getting to a point where we start to get oscillatory behavior. The population can jump back and forth. And there's a lot of implications then for ecological modeling. Is a population really heading to extinction, or is it undergoing some sort of oscillatory behavior? These have been observed in many populations, where the populations of different species, rabbits and lynxes, a famous example, where the populations oscillate dramatically depending on the population of the rabbits and the lynxes, the bobcats. And that's interesting. And then you get to a certain point when you can actually get now more complicated, what are called period doubling, new oscillatory behavior, and you will get farther and farther, and eventually you get chaotic behavior, meaning this will never repeat. This incredibly simple model will never give you a repeating signal. And if you did that Fourier analysis, you would find there's no fundamental frequency to it. Now, let me demonstrate how this now is going to affect our concept of epistemology, how we know. So we'll take the same model here, start some value, and now I'm going to put it into the chaotic regime. And what we've plotted here are there's red and black or gray. And the difference is our initial value was 0.492, and then the gray is 0.493. And you can see after 15 generations, you're diverging and you're getting different behavior. So let's make that even a stronger effect. All right, here. So after only 10 generations, you're getting very different behavior. So you say, well, okay, that's still, we could probably measure that difference, but let's make this really small. This means we have 0.492000001. And again, after 30 generations, the results diverge. So this demonstrates what's called extreme sensitivity to initial conditions. We'd have to measure it. We'd have to know our initial variables, in this case, just the population. But this could be the solar system, which means you'd have to know the mass and the position of and the velocity of all the planets with incredible precision. And the answer is that's not possible. But so that puts a fundamental limit how far we're going to be able to predict in the future for some type of systems. So even if we have a perfect model for a system, there's a limit to how far in the future we can make an accurate prediction because of the limits of our knowledge of the initial conditions. All right, if you say, all right, that's a practical limit, but is it a fundamental limit to our knowledge? Well, there's something called the Heisenberg uncertainty principle, a great name taken on by Walter White in Breaking Bad. He called himself Heisenberg in tribute to this great scientist. He said there's actually, he proved mathematically, there's a fundamental limit to how precisely we can know the position and momentum, how fast an object is moving. So it's not a practical limit. It's not that you just can't measure it well enough. There's a fundamental limit. And so for a chaotic system, even that very small uncertainty will be amplified to the point where there's a limit to how far you can predict. So how far is that? Well, it means you can't infinitely predict into the future. There will be some limit how far you can go. And there are many examples in nature. Probably the most famous one is weather. Weather is believed to be a chaotic system. And in Jurassic Park, Jeff Goldblum eloquently explains the butterfly effect, that a butterfly flapping in Bangkok will cause a hurricane in the Gulf of Mexico. And he explains it to Laura Dern in the movie. It was a very good explanation, actually. However, it's not all bad news, because although you may not be able to make incredibly long predictions, there's limits to how well you can do it. It's also not random. So I'll show you here. This is what's called a phase plot. And it's these really beautiful diagrams. It's really showing how fast air currents are moving X, Y, and Z direction, right? If this were completely random, this would just all fill up. The line would go every direction, and eventually would just be a big filled domain. But in fact, you notice in this chaotic system, there is some underlying order to it. It means if you're here, this says you'd watch the system, it's going around and around and around. It means you can't predict if you start at an arbitrary point, maybe 6 months in advance or a year in advance, but you will be able to make short-term predictions because it's not random. If it were random, if it were in this point, it would just be as likely to go this way, this way, this way, this way. There is an underlying pattern to it. And so there's some good news, bad news here. The bad news, even if we have a perfect model for a system that is chaotic, there's a fundamental limit to how far in the future we can predict its behavior. The good news is if a system that appears random, it may instead be chaotic, which allows some predictability like the weather, but it does require us to get much more data. And there are some interesting questions now. People have posited that perhaps chaos is actually present in brain function, that it's not random. There could be a dynamical system, and being chaotic could have some advantages to be able to rapidly respond. I know almost nothing about neurobiology, but there's a lot of intriguing ideas from this. And I thank you very much for joining this presentation today.
Thank you, John. There's much to talk about and much that I think we can talk about together and across the different fields. I want to turn first to Anessa and see if we have any specific questions from students before we begin the more general question session. Anessa?
Sue, nothing from me. So Aaron has a few for you, though.
Okay, very good. Well, students out there, please continue to put questions in the Q&A and we will put yours up as soon as we receive them. We do have one. I see that there is one question now for looking at the list. One question for Willis. And Willis, the question was, how would you conceptualize the uncertainty of people who play the piano with no formal education?
It's an interesting question and a frequent question, I think, that I've considered. Some musicians are just innately, intuitively at a kind of genius level. They just hear music and can express it. They don't know how they're doing it. They just do it at a very high level. And there's some that have kind of an intuitive talent, but I'm getting back to that vocabulary thing again. Their vocabulary is like this. So what you hear them do for the first few minutes is really, that's great. Then after a few minutes, you realize, well, they're doing the same thing over and over. That may be an oversimplified way of describing what happens with people who don't have formal training, but there are some who have just this amazing intuitive grasp of what music's all about. The great Charlie Parker, who is considered the greatest bebop saxophonist of his time, was really not that well schooled in terms of basic music fundamentals theory and the like, but he did some of the most innovative and complex musical things. It's really quite amazing. And there are lots of stories like that.
Thank you. We now have a question for Emily, and that question concerns the time difference between the first original survey and then the more recent one. Do you think that that could in some way account for some of the difference in the findings?
I think that's a really important question. If by time the person means that the original study was done in 1966, and then now it's obviously so much later than that, I think that was part of our problem as the research team, that this finding was still accepted just as though it were a fact that's just as fresh of any fact. And the lack of a clear replication attempt in the existing literature was one of the main motivators. And so we didn't necessarily believe that they were wrong. We weren't on a mission to say, oh, clearly these people are wrong, but on a mission more to say, what do we know about how memory develops in children in 2019, for example, than we did in 1966. And what's extraordinary is that they were still generally right in that young children don't rehearse as much as older children, but we were able to get a much finer grained analysis across a larger sample. And so I think the short answer is yes, it's partially different because so much time has gone by, but it's also verifying that part of that certainty is still there. I mean, this behavior of children held up over all these years.
Thank you, Emily. I see that we have a
question from a student, if
Go
I may.
ahead, Vanessa,
Yeah.
please read that.
So we have a student from Occidental College, and this question is for Dr. Pojman. When considering the limits of what we can know from the Heisenberg uncertainty principle, how do you factor this uncertainty into models? Is this limit different for different things that you're interested in studying?
Absolutely. I mean, to be able to have the Heisenberg uncertainty principle be relevant, you'd have to have an extremely simple system in which that level of uncertainty on the quantum level would play a role. So practically, we can't measure if you take a normal dynamical system like the weather or even some pendula in the laboratory, we can't measure things precisely enough to even worry about the Heisenberg uncertainty. So that's really much more of a fundamental question about is there really a limit to how far we could predict in the future? But practically, unless you're dealing with a very small system like the quantum level, it's not going to be directly relevant. Good question.
I see we now have a couple of questions for Professor Delony. I'll give you two, Willis, so you can bundle them. The first is the following. Is improvisation equally plausible in all vocabularies or better with some? Jazz is famously improvised, classical music less so, though back in the day there probably was more improvisation, particularly in the cadenzas included in earlier concertos. Are there differences in how well a vocabulary improvises, and how would one explain the difference? And then your second question is, does your classical playing of, say, Bach inform and inspire your jazz playing?
I'll answer the second question first, and that's an affirmative, enthusiastic yes. My classical playing informs my jazz playing, and vice versa. It just, you know, my brain seems to be wired that way, and so it's music, and that's just the way it works for me. As far as the other question, it's a very perceptive observation on the part of the questioner. Does a certain musical vocabulary lend itself better to improvisation? I'm not sure I can answer that. I just know that the jazz language is purposely geared towards improvisation. And until we got to the year 1800 or so, the classical or the European art music tradition was also heavily involved with improvisation. Beethoven was a great improviser. He practiced it. Mozart, as the questioner pointed out, improvised his cadenzas to his piano concertos on the spot. It was expected that a performer could do this. Audience members would sometimes submit musical themes on a scrap of paper and hand it to the performer, and the performer was expected to improvise a set of variations on that theme. Now, that particular part of the classical art, if you will, it's gone, it's long gone. But jazz musicians do that all the time. So whether it's more conducive, this vocabulary or that, I can't say. I can't say for sure. I just know what we do as improvisers is geared more towards certain specific languages and styles and vocabularies.
It's Wills, just to follow up on that, does it have something to do with the sort of canonical nature of the repertoire?
Yes, yes. I mean, these great composers who were great improvisers also wrote down these monumental artworks, the Fifth Symphony of Beethoven. I mean, Chopin was a great improviser too. But fortunately for us, they wrote down a lot of stuff, and it's hard for us to improve on that. So maybe that's kind of one of the reasons that in that particular style, the art of improvisation is gone, because we have this huge body of work. Why do I need to improvise like Beethoven? I'm just going to go play some Beethoven.
Right, who am I?
On that.
Who am I to fix Beethoven?
Right.
Unless I see we have another student question.
Yes. So this question is for Dr. Elliott and Dr. Pojman. How do you communicate the uncertainty of science to the general public? It seems like many people who are distrustful of science will take the idea of scientific uncertainty and use it to justify anti-intellectual sentiment.
Emily, you want to go first?
That is a really fantastic question. And I think that one of the things that we talk about a lot in the field of psychology is how to communicate our science more effectively, because everyone, for example, has a memory, right? And we all have sort of a sense of how our memories work, but it may not be the case that that is the correct understanding of how our memories work. And if we can, for example, help people to understand how their memory works more effectively, it improves their life. And so trying to, I think personally, not come from some superiority position of science, but let's improve your life position of science, and communicating that effectively, because that's part of what I think psychology tries to do.
John?
Well, first, I want to say that the kind of problems Dr. Elliott solves are the really hard problems. The ones we do in chemistry are so much easier because we have so much more control of the variables. You know, we can, even any kind of living system is so much harder, let alone a human being. So we can take chemicals, if you use the same chemical, you're going to get the same results. I should emphasize that when I'm talking about uncertainty, the epistemological, our ability to know, is related specifically to a type of system called a chaotic system. So mostly when we make technological things, we make them so they're not chaotic. We don't build airplanes that are chaotic. We don't run power plants that are chaotic, because they're going to be very hard to control. Although there is some area of using chaos to control chaos and maybe get an advantage. So it's a bit subtle. We need to express that there can be sometimes situations where it's hard to predict, but it applies to certain types of systems. And so I would often, even when people ask me, say, well, how do you really know for sure that something's correct? I say, I don't. Science doesn't know things for sure. It disproves things for sure. But the most beautiful example is this recent Mars rover. I mean, that's a highly complicated dynamical system. But if you watch this movie of them able to land this thing, you know, millions of miles away, and have a video coming back of it landing and coming down, you say, you know, maybe in principle, we can't predict the path of Mars indefinitely in the future, but we sure can land something on Mars today. Great question.
John, as a follow-up, what about this? What is the status of the term probable? I mean, in which cases can we just say our results are probable, and when is that not enough, insufficient?
Well, I would distinguish sometimes you have systems that are inherently, we call stochastic, random, and then you have a problem where you do have just probabilities. You can say the probability of the next generation, say, of species. In a chaotic system, you're going to have much greater certainty, but you're going to have your level of certainty will degrade with time. So there really are different classes of problems. The good news is things that would seem random, like I mean, the one of the expressions people make that drives me crazy is, oh, if you don't like the weather in Louisiana, just wait 5 minutes. Like, no, every time a cold front comes through, I rejoice in a thunderstorm, because I say this is exactly what you'd expect. A cold front comes through, we get thunderstorms, and it just validates my whole worldview. So I love extreme weather, because you wouldn't randomly predict what's going to happen tomorrow, that you're going to have an extreme weather event. But we knew it was coming last week. So the weather may be chaotic. We may have difficulty with very long-term prediction, but that doesn't mean we can't make short-term. And I should distinguish that between, say, climate modeling, which is a very difficult problem. It's one thing to talk about, say, average behavior over the whole climate. That's different than knowing what the temperature will be in Baton Rouge, say, in 100 years on a given day. That becomes, it may be in principle impossible to do it, but we don't need to do it.
We will have, by the way, the state climatologist, Professor Kine, on our series in a couple of weeks. And so we can also ask him to talk a bit more about precisely that problem. In the meantime, we have another question here for Professor Delony. As a person who has done some solo music performances, I'm fascinated by what to do when you make a bad mistake. I appreciate your advice, and I've sometimes done that. But in contrast, Paul McCartney, something just happened to the questions as I was reading it. Here we go. Paul McCartney once had a senior moment playing the piano opening to Maybe I'm Amazed. He froze and could not think of what notes came next. He decided to use humor. He said, "What comes next? Don't worry, I can do it." How about fessing up that you botched it and using the humor to cover up with the audience?
I know what comes. If I'd only been there. I love that song. I've played so many concerts in my life where I wish that I could have a few moments back to do over again, but we're human beings. And I could advise the questioner, if you're playing and you hit one of those spots, just keep going. Play something. Again, you've got some vocabulary there. If you've got the courage to express some little musical bit of your vocabulary, you'll find your way back. Or maybe not. Just keep playing something, play a nice cadence and finish it. We have to have a certain amount of courage sometimes when we go out on a stage as performers. It's the butterflies are always there. I still experience them every time I get ready to perform. I think they're productive in my case. It focuses the mind a little bit, but once I get out there, it's fun. It's what I do. But I'm no longer surprised when something happens, because it's happened. Years ago, I was playing with the Baton Rouge Symphony. I was playing the Gershwin Piano Concerto. The second movement is structured in the form of a blues. Each section lasts 12 measures, like a blues tune. And I got hopelessly lost. All I could think was, I'm lost, but oh, this is a blues. So if I just play a blues in this particular key, I'm going to find my way back, which is what I had to do. It didn't sound great, but at least I didn't, shrink into a puddle and leave the stage. Had to keep going. People do that all the time. Much worse has happened to me in my life than forgetting a note or two. So it's not a big deal. Just keep going.
An excellent life lesson. Absolutely. Unless I see we have another question or two from students.
Okay, this is the first one to Professor Pojman. How do you reconcile the creation of instruments like planes that are meant to be certain with a chaotic system? Is there some degree of certainty that we must attain?
Absolutely, and that's I showed you an example. We have that map, we call that logistic model. I was changing a variable there, and the key is when you're designing something is make sure you don't have that lambda in the chaotic regime. And so engineers have been well aware of this. When they design systems, you can have oscillatory behavior, chaotic behavior, not so much chaos originally, And engineers know you try to avoid those regions. So when people design airplanes, they design power plants, we want to design them in a region that's not going to end up into a chaotic regime. I mean, for example, the electrical grid is a highly complicated electric dynamical system. I know almost nothing about it, but it's very, very important to design it in such a way that a perturbation like a snowstorm won't wipe out the grid of the nation. So it's important to design systems that are robust and not going to be sensitive to initial conditions.
And that's another.
Yeah, I have one more. Also for Dr. Pojman. This question is motivated by your brief point a few minutes ago about the study of living organisms being tricky. Is it possible for chaos theory be applicable to human behavior?
There are people attempting to do that, and people smarter than I trying to do that. Certainly looking at brain, for example, looking at EKGs or during certain events, maybe Dr. Elliott knows, I'm sure she knows more about it than I, to try to analyze it as, is it random brain activity, or could it actually be chaotic, and could there be some particular advantage to it? So I think it's possible. I was thinking more of just simply things that, things that just die when you don't want them to, more dramatic effects. But I think there's certainly parts. It's certainly true in some cardiac behavior is known that there can be some, what may look like random behavior is not. And there are cardiologists attempting to use these theories. Yeah, great insight.
I'm going to take one more question for Professor Delony, and then if any of the panelists have questions for each other, I'd like to give you the opportunity to do that before we close. Here's one for Professor Delony. How does musical improvisation work in a group? Your story about Miles Davis and your own experience in a jazz band demonstrate it's possible, but how can the rest of us non-jazz legends sync our improvisation with a group?
Well, that's a very involved question, but very relevant. I get back to our vocabulary analogy. When I'm improvising with my colleagues, we have a kind of a shared template that we're going to follow. We play a certain number of measures, a certain harmonic sequence. Recall I talked about the blues progression. The blues progression has some specific chords that we play, so we know what that sequence is, and then within that framework, which we all know, then we can start to interact, kind of converse musically. So I would ask the questioner, what vocabulary can you and your colleagues share? Could it be just one chord? You might have a bass player that can play that. I don't know, but just one chord. Limit your choices. Narrow it down so that everybody can succeed at some particular level. That's what we do with our students. We find what they know, and then we make them do something with what they know. And if it's just one chord, that's fine with me. And
Willis, what do you do when someone goes off the ranch? Just let's say improvs for much too long, or takes the piece in a completely selfish direction.
Well, they can't go on too long. As Wynton Marsalis once said, you need to mind your manners. You don't need to solo forever. You need to give the other guys a chance to express themselves. You can get self-indulgent if you're not careful, so mind your manners. And there's a kind of give and take on the bandstand with that too. I've been on the bandstand with people who tend to play lengthy solos, shall we say. And the piano player is just over here trying to make everybody sound better, if at all possible. But my wife says that when that starts to happen, she sees my chin start to jut out, and she knows that I'm perturbed. We're humans, it's a human activity. Jazz is a great metaphor for human interaction. Chamber music too, in a classic.
Fantastic. Now, would any of the presenters like to pose their own questions?
Sue?
Yes, go ahead.
I have a question for Emily. Emily, intrigued by, I've never seen studies that were done cross-culturally. I'm wondering how are these results also can be confounded by socioeconomic status? You know, say the early childhood education, how much that affects kids who would be, well, I don't know, but that's, I'll just leave it at that.
That's an excellent question. And so one of the things that we realized once we started getting that call for participation, even though we were thrilled that it was so broad and that it included 6 languages, it was a particular sort of Western-based sample. You know, so we did have someone in Costa Rica, we did have someone in Turkey, but most of it was the US, Germany, France, you know, et cetera, like places. So we didn't have a full range to really answer that question. So I think the best answer to your question is yes, socioeconomic status has been shown to have implications, for example, with childhood vocabulary development. How many words are spoken to the child can have a really big influence on later academic performance. In that, looking in a true cross-cultural sense, as researchers can do, you have to get a much different kind of sample. So in that regard, we can't really address it because our sample was as big and as broad as it was too similar in that domain.
Can I follow up with, I think someone was asking earlier about the time difference. Could children be different in the 60s? I mean,
yeah.
I mean, certainly I've seen people who generational cannot use a computer because they had hand-eye coordination thing. They just never grew up using a video game or anything like that. And it just seems to be, you grow up learning it and kids can do it very fast. So is that another possible?
That's an absolutely a good question. And so one of the other wonderful things about this collaborative team is that we range from postdocs just finishing graduate school to well-established professors who, you know, very well remember the original work from the 1960s. And so that has also been brought up that, for example, the ways in which children are now taught that it's appropriate to, for example, in a restaurant, look the server in the eye and place your order. Whereas perhaps in the 60s, that would have been considered out of line for a child to speak so directly to an adult. And so that there's been cohort differences. So again, yeah, definitely. I mean, so that's one of the great things that this research, again, as big as it was, as long as it took, all it has done is spawn more questions, because now we want to know all of these other things. Well, why this? And what about this limitation? And so what our hope is that since this data set is publicly available and free, people can download it and do different analyses than we did. People can do follow-ups and draw upon our design, use our materials and build and do something different with them. So that our hope is that this will also spawn many additional studies so that we can continue to answer these questions.
Great.
Emily or Willis, do either of you have questions for your fellow panelists?
Very scientific question, but Emily, your children were part of this too. And so, you know, as a parent whose kids are all grown, but as a grandparent whose kids are emerging into those years where they could potentially be case studies, it's not a scientific question. What was it like working with family members?
It's wonderful. So my children, just to make sure that's clear, they're not in the final data set. They were in the pilot testing of the materials, because it's very possible that living with me, they heard me talk about the study and maybe had biases that I didn't even mean to pass on to them. So while they helped me develop the materials, they were not included in the final sample. Because I do think that would have been a problem. But generally speaking, what we did is we recruited through East Baton Rouge Parish Public Schools, through schools that were literally convenient. So for example, there's an Episcopal school that's close to campus. So we tried to, again, from a socioeconomic status standpoint, not get every kid from the same school, but recruit more broadly across Baton Rouge. And we had also probably some selectivity in our sample in that regard. Some families are perfectly willing to let their child either stay after school at the school and have a researcher come and sit with their child. Some families think that that's a very questionable activity. And so the other thing that we have to constantly think about as scientists is there's such a selection bias in our sample. So we want to generalize and say these children represent all kindergartners. But maybe that's not true. These children represent the kindergartners of families who were willing to have their kids be in a study. Now, in some of the cases, especially like in Geneva, for example, it was entire classes, like all of the kindergartners at a certain school, like the entire school consented, right? Whereas in other cases, it was individual parents consenting. And so there's probably some selection bias to think about too.
Let me thank all of our panelists so much for this wonderful set of discussions, which will lead to more and further discussions in the next few weeks. I hope we look very much forward to continuing this discussion across the arts and sciences, a discussion that reminds us just how powerful and inspiring both uncertainty and our attempts to master it can be. Thank you very much for all of your attention. Thank you for your great questions. Thank you, panelists, for all of your insights and your good humor and your life advice, as well as your scholarly advice. Thanks, everyone, and good night.